Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be looking at some example problems with centripetal force. So in case you missed the last video, or you just need a recap on what the equations are, here are the equations we need to know for centripetal force. Number 1, centripetal acceleration, A sub c, is equal to v squared over r. It's the velocity over the radius of your circle. We have the equation F net, comma c, the net centripetal force, which is equal to all the forces pointing in towards the center of your circle minus the forces pointing out, and that's equal to mv squared over r. So basically what I'm saying is if you have some circular motion like this, and you have this, you're looking at this point here at the top, you have a force pointing in at the bottom, you have a force pointing out at the top, you literally set up the equation like this: force in minus force out equals mv squared over r. So that's the setup. And now let's look at some example problems. A lot of times centripetal force problems involve amusement park rides. That's because Ferris wheels, loops on a roller coaster, the gravitron, the roundup. There are so many examples of rides that just move you in a circle that most of the time we look at those for the questions. So let's say I'm on a Ferris wheel, and the Ferris wheel looks like this. It's a big Ferris wheel, and pretend that's a perfect circle for me, please. I'm going to tell you the radius of this circle is 25 meters. And let's say you're moving at a constant speed of 3 meters per second while you're on this ride. My question is going to be, what is the normal force at the points A, B, and C? And what are points A, B, and C? Well, I didn't draw them yet, so give me a second. Point A is here. Point B is at the top, and point C is here at the side. I just need to give you one more piece of information. Let's say this cart and the passengers inside the Ferris wheel carriage, let's say the mass of all that is 500 kilograms. Okay, so let's start with point A. For point A, I have only two forces that I need to worry about. I have the force of gravity, which points down, mg, and I have the normal force, which points up, Fn, just like that. Normal force points up, by the way, because it's coming from your seat, and your seat is below you, so it's pushing up on you. So these are my two forces. I then say F net, comma C, equals forces pointing in towards the center, that's Fn, minus the forces pointing away, so minus mg, and that's equal to mv squared over r. I have all these variables. This is a very easy problem. Fn minus m is 500, g is 9.8, equals mass 500 again, times the velocity, which we said was a constant speed of 3. So 3 squared divided by the radius, which is 25. So then Fn minus 500 times 9.8 is 4,900. And the right side, if I plug that in my calculator, then I just get 180. So now if I want to solve for the normal force, I just add 4,900 to both sides, and I'll get a normal force of 5,080 newtons. Which, by the way, in case you're wondering what that means, the normal force should have been 4,900 if there was no centripetal acceleration at all. But since we added the 180, you feel a little bit heavier when you're at the bottom. Not much, like 180 is small compared to 4,900, but you will feel a tiny, tiny bit heavier at the bottom. And that was for point A. Now let's do for point B. So I'll just redraw the picture. I'm looking at point B now, which was at the top. And at the top, I have a force of gravity pointing down, mg, and a normal force still pointing up, Fn. The free body diagram didn't change. That's still the same. But what does change is my equation F net comma C, all the forces pointing in. Now it looks like mg is pointing in. Even though it points down, it's going to be positive because it points towards the center of my circle. And then minus Fn, because that points away from the center of my circle. That equals mv squared over r. And all the numbers are the same. Like this is still 4,900 for mg. Minus Fn. The right side is still 180. You can plug that in a calculator. The numbers didn't change. But now if I want to solve for Fn, I would add Fn to both sides, and I would subtract 180 from both sides, and I would get the normal force Fn equals 4,900 minus 180. That's 4,720 newtons. In other words, you feel slightly lighter than normal when you're at the top because you're subtracting the 180. And finally, we still have to worry about location C. Location C, I'm not going to lie, is a trick question, honestly, but you don't know that yet. So if I draw my free body diagram for point C, I have a normal force going up, just like before, and gravity points down, just like before. This is kind of a weird question because it doesn't look like normal force or mg. It's definitely not pointing towards the center, but I would also say it's not pointing away from the center either. And the reason why I say that is because this is the direction of force in, that's the direction of force out. You'll notice that it's perpendicular to both of those. In other words, we're not going to use centripetal acceleration because it's not going to work for this. Neither force points towards or away from the center of the circle. So then what do we do? Well, if we go back to our other physics examples we did previously, we still have Newton's second law. We're just going to use F net, not C, but F net comma Y. Because if you look at the Y direction, for the Y direction, it's all the forces pointing up minus the forces pointing down equals ma, not mv squared over r, just ma, Newton's second law. Force going up is Fn, minus force going down is mg. That's equal to ma. We don't know the acceleration, which is a lie. I do know the acceleration. It's not the centripetal acceleration. It is the acceleration right here at that point going up and down. Now, you may not know what it is, but the fact that this is constant speed, I said at the very beginning, constant speed, it means the acceleration, at least in the y direction, the acceleration is 0 there. Again, the acceleration is not 0 for centripetal, but it will be 0 for the y direction. And that's very nice for us. That means Fn minus 4,900 just equals 0. It looks like the normal force equals 4,900 newtons. In other words, when you're at point C, you feel the exact amount of weight that you normally feel, which is 4,900 newtons mg. Now, I'm not done with this problem yet because there's still one question to be asked. There has to be some force pointing towards the center, or else the object isn't moving in a circle, which I promise you it is moving in a circle, which then begs the question, what's the force pointing towards the center? I want you to think if you're actually on a Ferris wheel at point C on the ride, you're on the side of the ride, there must be some force acting on you, and it's not gravity and it's not normal force that causes you to keep moving in a circle. Do you know what it is? The answer is static friction. And the reason why it's static friction is because you're not moving on your seat, like you're in place on your seat. And if there was no friction on this ride, you would fall off, which thank God for friction, right? Now, if you wanted to, you could actually solve for friction. I'm not going to ask you to do that. But if you are curious, the answer is static friction just equals mv squared over r. You wouldn't even use that equation. Don't use mu(s) times the normal force. That's not even going to work here. Because the only time you said equal to this is when you're talking about the max static friction, which I'm just not talking about it right now in this scenario. And I'm not going to dive into this because this is not a lesson on friction. This is a lesson on centripetal forces. So if you wanted to solve for the frictional force, it would be the mv squared over r, which was 180 newtons we said earlier. So now for the next example. The next example, you are on a roller coaster and you are going to be making a loop right here. Now, just so you know, actual loops on a roller coaster are not a perfect circle. They're actually more like a teardrop shape, and there's a very good reason for that, which there's other YouTube videos explaining why that is. I encourage you to check them out, especially if you like roller coasters. They're pretty interesting. But we're not talking about the teardrop shape. We're going to talk about the perfect circle example here, because that's just going to make it easier for us. And let's say this roller coaster loop has a radius of 12 meters. And what I want to say for this problem is, imagine you're on this roller coaster, right? And if you're not going fast enough at the bottom, you need to have a pretty good speed when you go into a loop. Why is that? Because if you're going too slow at the top, you're just going to fall out. Now, of course, you're not actually going to fall out because you usually have the overhead harness on you. But let's say there's an example like there's this roller coaster in Hershey Park in Pennsylvania, where I'm from. And the ride is called the Super Duper Looper. As far as I know, it's the only roller coaster in the world that doesn't have an overhead harness for a loop. It's literally just a lap bar. And when the ride came out in like the 70s or the 80s, they literally had t-shirts that said, "I survived the Super Duper Looper," because it was the only roller coaster that didn't have an overhead harness. It was just a lap bar, which means if you're not going fast enough, you're going to fall out of that ride. Now, the good news is that ride's been in operation for like 50 years now, and no one's fallen out yet. And that's because whoever designed it was very good at physics, and they knew about critical speed, which is what I'm going to talk about right now. So critical speed is essentially the speed that if you go any slower, you're going to fall off the ride. What that really means to you is that the critical speed is when the normal force equals 0. Why is that? Because if you are falling out of your seat, well, then you're not touching a surface anymore, that's for sure. And if you're not touching a surface, then the normal force is 0, because that's where the normal force comes from, a surface. So if you want to solve for the critical speed, you just want to set the normal force equal to 0. That's the secret for any of these questions. And my question is, what is the speed that you have to have at the top in order to not fall out of the ride? Now, I gave you the radius. I'm not going to give you the mass. The mass is unknown, which whenever that happens, it means you just write variable m. It's not a big deal. Just write variable m. And so now let's find the critical speed. So again, I'm going to say F net, comma C equals the forces pointing in minus the forces pointing out. For this example, we're looking at the top, the free body diagram for the top. I don't care about the bottom. And if I think about the forces acting on it, I've got mg going down, and normal force is 0, so I'm not even going to write it. But if there was a normal force, it would still point down. It would not point up. Why is that? Because technically when you're on the roller coaster and you're at the top of the loop, the floor is above you. And if the floor is above you, it's pushing down on you for the normal force. So if we did have a normal force, then it would be pointing down just like gravity. The equation should be mg plus Fn, and then you just plug in 0 for Fn. Anyways, you set that equal to mv squared over r, because that's what we do for centripetal force problems. And then mg, which we don't know the mass, so you just write m. G is 9.8 equals, again, we don't know the mass, so you just write m, times v squared, which is what I'm solving for, divided by radius 12. At this point, you can say mass cancels, which it does. And if you want to solve for v, then you need to first multiply both sides by 12 equals v squared. And then you're going to take the square root of that. So I'll plug this in my calculator, and we'll see what we get. I got a final speed of 10.84 meters per second, which doesn't sound that fast for a roller coaster. As a matter of fact, that's only about 22 miles an hour, so it's not that fast. But what I will say is that that's a good thing, because it means that even if the ride's operating slower than normal, you're certainly going to clear that loop. That's for sure. And so that's it for that problem. Now let's just look at one more example. This is a famous problem in physics. Let's say you're driving in a car. I'm going to draw a top-down view for this problem. So you're looking at, a road like this. It's just a normal curved road. It's level. It's not a banked curve problem, which is another physics problem that we could do, which in my opinion is like one of the hardest questions in all of physics, is the banked curve example. But this is just a flat road. You're looking at it from the top. You're a car driving on this road, and you're going at some speed v, which is what I'm going to be solving for. Now, even though this road isn't a circle, you can kind of imagine it like a circle. And let's say the radius of this turn is 40 meters. Now let me give you some values. I'm going to give you the coefficient of static friction and say it's 0.6. I'm going to give you the coefficient of kinetic friction and say it's 0.4. And my question's going to be, what is the fastest speed you can take this turn without sliding off the road? So we can all picture this example. If you're going too fast, you're going to fly off the road, and that has to do with friction. The reason why is because if you didn't have friction, well, that'd be like driving on ice, and you do not drive very fast on ice because you're going to be sliding all over the place. So the first thing I should do if I want to solve this question is I need a free body diagram. So I'm actually going to stop myself there because the free body diagram's kind of weird. Normally I say mg goes down, but isn't this a top view? So that wouldn't make sense to say it goes down. Actually, the force of gravity goes like into the page. I'm not even sure how I draw that. And the normal force is actually coming out of the page because the road's beneath you of the car, so the normal force is going to point in the opposite direction of gravity, of course. What I'm trying to get at here is the top-down view is not good except to just visualize the problem. So we are allowed to draw a front view. I will do that. I think that's going to help me a lot. And if I draw a front view, then here's my car on the road. Okay, got my little headlights and I'm cruising, I'm driving. Now I can say gravity points straight down and the normal force points up. That's great. But it still doesn't answer the question of what force is causing me to move in the circle. There must be a force pointing inwards from the circle. What force is it? Well, you probably have a good guess. You're probably going to say friction because I gave you coefficients of friction here. And if you think of it logically, friction is going to keep you on the road in the circular path. So yes, it's definitely friction. Now I gave you two coefficients. I gave you kinetic and static. I did that on purpose. You only need one. You need to tell me which one you need. And so of course, the car is moving, so we're going to use kinetic, right? No, we will not be using kinetic. I agree with you, the car is moving. However, is the car moving side to side? No. I repeat, is the car moving side to side? Yes, the car is moving forward and backwards. I agree with you there. But is the car sliding side to side? Is the car sliding left or the car sliding right? No, because that means you're sliding off the road, and we specifically don't want that. Why is your car not sliding left to right? Because of static friction. You're not moving left and right. And even if that explanation doesn't make sense to you, I promise, if you use mu k, the kinetic friction, you're going to get the wrong answer. You need to use static friction, which is 0.6. And that is the force pointing towards the center. I call it Fs for static friction. And now if I want to set up my equation, I would say F net, comma C for centripetal, is all the forces pointing towards the center of the circle, which if I go back to my diagram, there's only one force, Fs. There's no force pointing out. Gravity and normal force don't point in or out. They actually point in the y direction, which is a separate equation entirely, just like the first example with the Ferris wheel. So the only thing I have in F net C is Fs, the static friction, and that equals mv squared over r. So I don't know the velocity. I need to solve for it. I gave us the radius. I didn't give us the mass, and I'm not going to for this problem because I'm a jerk. And I don't know static friction either. There's a whole lot of things I don't know. So, sounds like we're in trouble right now. Luckily, there's another equation we can use. Whenever you get stuck in physics, especially a force problem, all you need to do is write the equations you know, and we do literally every single problem. Like we just did F net C. The next thing that would be logical to try is F net Y. And the reason why is because in the Y direction, we have these two forces here that we can consider. So for F net Y, I always say the force is pointing up minus the force is pointing down. That's going to be Fn minus mg. And again, it doesn't equal mv squared over r. It equals ma. And is the acceleration 0 again? Think about that. Is the acceleration 0 for the y direction? The answer is yes. Because is your car moving up or down? No, definitely not. So the acceleration is 0 for the y direction. That's great because I can then say the normal force equals mg by adding mg to both sides. Now, again, I don't know what mass is. I don't know what gravity is. And why do I even care about the normal force? There is a very good reason why you care about the normal force. It's because what's static friction equal to? We have an equation for it. Fs is less than or equal to mu s times the normal force. Ah, there's the normal force right there. We can plug that in. Not so fast. Think about this. Static friction is the less than or equal sign because it's not always equal to. You can't always use this equation unless the wording in the problem says that we need the max static friction, because remember, only the max static friction is when I use the equal sign for this equation. Otherwise, I cannot use this equation. But if I look at the wording in my question, what is the fastest speed you can take this turn? If I want the fastest speed, I'm going to need the max static friction. So I am going to use this equation. I love making you think and double and triple crossing you. But yeah, we get to use static friction. So static friction force equals mu s, which I said was 0.6, times the normal force, which I said is mg. I'll just leave it like this for right now. But now I can plug that in for Fs back in our F net C equation right here. So what I'm saying is 0.6 mg equals mv squared over r, which was 40. It looks like the masses cancel. Isn't that great? And so then I can say multiply both sides by 40. So 0.6 times g is 9.8 times 40 equals v squared. So the left side, plug in my calculator. I get 235.2 equals v squared. And then I'll just take the square root of that. And it looks like I get 15.3 meters per second. That's the fastest I can take this turn without sliding off the road. In case you're curious, that's about 35 miles per hour, which means that the speed limit for this road would probably be around 25 miles per hour because you're going 10 miles per hour over anyway. Okay, so that's going to do it for today's lesson on centripetal acceleration and centripetal force. Of course, there are so many more problems I could have done. I didn't have nearly enough time to do all the ones I wanted to do. So luckily, there's a ton more that exists on YouTube or on Google. You can find them. I encourage you to. Thank you all for watching this video. I hope you have a great rest of your day, and I'll see you in the next one. Take care. Bye-bye.